Today's lesson will be our last on covalent compounds. Same learning goal we've talked about for both ionic and covalent compounds. Through inquiry and exploration, students will be able to understand that bonds hold elements together in specific ways to form new compounds that are then represented by specific chemical formulas and nomenclature. So at this point, you already know how to write chemical formulas for ionic and covalent compounds, as well as name them. And I've got a secondary classwork assignment for you on Edline that will really help you prepare for your test. I'll show you exactly where it is. That may be something we can do afterward. Today, what we're really going to get into is looking at interactions between molecules. Not the bonds that make up a compound, but rather the forces that form between molecules. And this is particularly important to understand properties of compounds. So we've been talking about covalent compounds for a while now, and today we want to talk about intermolecular forces, which are abbreviated IMFs. And these are forces of attraction between molecules. And again, I'm not big on words because I think they can be a bit much to digest. For example, if we had a water molecule we know water has that bent design, 2 atoms attached, 2 lone pairs in regard to the central atom. This right here is a covalent bond that represents 1 shared pair of electrons. This is an intramolecular force. Intra, within, very strong. If we had another water molecule here, same bent design, there is some interaction between the water molecules. And this interaction is known as an IMF, an intermolecular force. So between 2 molecules. And intermolecular forces determine physical properties of liquids and solids. It also helps explain why some substances are gases at room temperature where other substances are solids. Now think back to biology. Do you know specifically what this IMF is called? All right, so that's something we'll get into today. And I think when you hear it, you will recall it. So we're going to talk not about intramolecular forces or bonds, but rather intermolecular forces. And if you look at the periodic table shown here, group 17, you know, as your halogen family. In this group, you have gases at room temperature, a liquid at room temperature, and a solid at room temperature. And that's all based on the intermolecular forces between these substances. Depending on the intermolecular force strength, you can determine if your substance is a gas, liquid, or solid. In addition, intermolecular force strength will lead to differences in boiling points, melting points, vapor pressures, etc. A lot of the different properties that we'll explore later in the year. The distinction between inter and intra, clear, because that's an important distinction. Yes? Okay. Now this is a very complicated topic. I have a lot written down here, but we're going to keep it very, very simple. This is part of the honors curriculum. I think it's a little bit challenging. Again, I'm going to try and keep it simple, but I think it will especially help you if you take college chemistry in college or AP chemistry here. So there's a whole big wordy thing here, but let's keep it very simple. We have water molecules here in the liquid state, and I can't really stop it at this point until I run it, but let's grab one of those little guys right there. The red ball is the oxygen, and the two white balls are hydrogens, and they look like little Mickey Mouses moving freely in the liquid state. Now I'm going to run this, and you're going to see some of the particles fly off from the liquid state into the gaseous state. The particles in the liquid state move. Those water molecules move. In the gaseous state, they move much, much faster, and that's because the intermolecular forces between the water molecules are broken, and into the gaseous state the water molecules go. And you can see again the difference in free movement, if you will, here, with no intermolecular forces between the particles. Here there still is some. In solid water or ice, you'll see greater intermolecular forces, and we'll look at that in a minute. In terms of what's written here, it says, as a liquid is heated, the kinetic energy of its particles increases. We know that temperature and kinetic energy are directly related. At the boiling point, the energy is sufficient to overcome intermolecular forces, and the particles pull away from one another and enter the gas phase. Boiling is a good measure of intermolecular forces. The higher the boiling point or the melting point, the stronger the intermolecular forces. So for substances that boil at higher temperatures than others, they have stronger IMFs, and we're going to take a look at that. First, we're going to look at ionic compounds. Ionic compounds are comprised of what? Two nonmetals, or a metal and a nonmetal? Metal and a nonmetal. Ionic compounds have higher boiling points and melting points than covalent ones, and that's because they have stronger forces of attraction. The forces of attraction that hold ionic compounds together are known as interionic interactions. In red, I didn't have that listed there. I've thrown it in now. Please add it to your notes. So the force of attraction between sodium chloride, interionic interactions, not the force between a sodium ion and a chloride ion. Those are ionic bonds. But when you've got a whole bunch of sodium chloride there, you have interionic interactions, and they are very, very strong. Stronger than the IMFs for covalent compounds, and as a result, if you looked at this table here, ionic compounds boil, these two, about 800 degrees Celsius, melt in the 14 to 1500, I'm sorry, I said that backwards. They melt in about the 800 degrees Celsius range. They boil around 1500 degrees Celsius. Now look at the covalent compounds. What can you say about their melting and boiling points compared to ionic compounds?
They have lower melting and boiling points.
Absolutely. Covalent compounds have lower melting and boiling points than ionic compounds. Don't even expect you to memorize that, but if you saw the table, you could interpret it. Very, very simple this year. The IMFs we're going to talk quite a bit about today are the IMFs, intermolecular forces that can exist between covalent compounds. Now let's think about this. With covalent compounds, we said they can be nonpolar covalent or polar covalent. And you know how to determine polarity. The first type of intermolecular force is known as a London dispersion force, named for Fritz London. This is the weakest of the intermolecular forces. All covalent compounds, nonpolar and polar, have London dispersion forces, abbreviated LDFs. Nonpolar covalent compounds only have LDFs, and we'll illustrate that to you. Let me show you what happens with a London dispersion force. For example, we have two unpolarized molecules. Give me an example of a nonpolar covalent compound. We can do it simpler. Which of the following is nonpolar covalent? The carbon tetrahydride, and this actually has a special organic name known as methane. Okay? This is nonpolar covalent. All the bonds are nonpolar. So this is a nonpolar covalent compound. Nonetheless, there is some type of force of attraction, not necessarily between the hydrogens, but between these two methane molecules. For a nonpolar covalent compound, the only intermolecular force is London dispersion forces. And these are the weakest IMFs. Neither of these compounds has a dipole moment, because this is a nonpolar bond, as is this, this, and this. So they don't have dipoles. But when they get near one another, they induce temporary dipoles in each. And that's what we're going to take a look at here. We have two unpolarized molecules, let's say two methane molecules. Look what happens when they get near one another. They have instantaneous dipoles. Their proximity adjusts the electron clouds, and now they have instantaneous temporary dipoles, because as the molecules move away from one another, those dipoles are gone. So the interaction between the two is known as an LDF, a London dispersion force, the weakest of the IMFs. And you can see that as well here.
In solid carbon dioxide, dry ice.
And let's look at carbon dioxide just for a sec, because this one's a little bit tricky. with carbon dioxide, CO2, remember this is one of those tricky wicky molecules because you've got a dipole here and a dipole here, yet carbon dioxide is nonpolar covalent. Why would carbon dioxide be nonpolar covalent?
The dipoles cancel out.
How come? The dipoles absolutely cancel because the molecule is
Oh, symmetrical.
symmetrical. Perfect. So carbon dioxide is a nonpolar covalent molecule because the dipoles cancel with the perfect symmetry. So this is a nonpolar covalent molecule, and that's what they're showing you here. Ooh, what happened to my poor little thing? Get back.
Dry ice.
I'm gonna
Non-polar molecules are arranged.
I'm gonna start it again. It looks like it's messed up. Here we go. So here's the carbon, oxygen, oxygen. So you have a lot of CO2s in there.
In solid carbon dioxide, dry ice, non-polar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
All right, so the only type of IMF in a nonpolar covalent compound is what? LDFs. All right. There's a lot with LDFs. I'm not going to go into it. I think it's too advanced for you. The only type of IMF in a nonpolar covalent molecule is an LDF. So when you're asked about forces of attraction, what type of IMF there is, determine if the molecule is nonpolar or polar. And if it's nonpolar, the only type of IMF it has is LDFs. Now, we said that all covalent compounds have LDFs. So polar covalent compounds have LDFs too, but they have an additional type of interaction known as a dipole to dipole force. And what you're going to see is that the permanent dipoles align themselves in a particular fashion. Shown here is hydrogen chloride. We're going to draw this out a little bit better. So our hydrogen chloride is right here. We said this is a polar covalent molecule. Which atom is more electronegative, the H or the Cl? Cl is correct. So the dipole is in this direction. That is partial positive here, partial negative on the more electronegative atom. And you'll see that the HCl molecules align themselves partial positive, partial negative, partial positive, partial negative. And the force of interaction here, the IMF, is known as a dipole to dipole force. Sometimes we write dip to dip, where this one is an LDF. So HCl is a polar covalent molecule. Polar covalent molecules or compounds not only have LDFs, but they also have dipole to dipole forces. And that's why polar covalent molecules typically have higher melting and boiling points than nonpolar covalent ones, because in addition to LDFs, they have dipole to dipole interactions, and those dip to dips are stronger than LDF. There are a few exceptions to the rule, but we're not going to get into that. And again, I tried to write everything in your notes so you had it, but we're going to keep it very simple. So if your compound is polar covalent, which you know how to determine, you'll have LDFs and dipole to dipole interactions. Carbon dioxide is nonpolar covalent, so the only IMF that it can have is what? LDFs. And again, everything is written here as well. If you look at this diagram or this chart, we've got nitrogen gas, carbon monoxide, and oxygen gas. I'm going to draw carbon monoxide for you. It has a very unusual structure. This is one of the few times that carbon has a lone pair of electrons on its central atom. This is a polar covalent molecule. You've got a dipole right there. So if it's polar covalent, what type of IMFs does it have? LDFs and dipole to dipole. And so if we examine boiling and melting points for polar compounds compared to nonpolar compounds, you will see the following. Which substance has the highest boiling point? Carbon monoxide, the polar one, and that's because it has not only LDFs but also dipole to dipole. There is a special type of dipole to dipole force, and it is known as a hydrogen bond. And that was what I referred to initially. I didn't know if you remembered it, but I would think that you learned about hydrogen bonds very briefly in biology when you were talking about water and DNA. A hydrogen bond is formed between a hydrogen covalently bonded to an O, an N, or an F, highly electronegative atoms, and an O, N, or F on another compound. And water is the perfect example of hydrogen bonding and gives rise to many of its properties. So a hydrogen bond is an IMF in which a hydrogen atom covalently bonded to an N, O, or F in one molecule is simultaneously attracted to an N, O, or F of a neighboring atom. And again, maybe we should put that in again, because that's what you're looking for, an N, O, or F. Now, some textbooks will argue that hydrogen bonds aren't dipole to dipole. Some argue that they're strong dipole to dipole. But the bottom line is, if the substance can hydrogen bond, it also has dipole to dipole and LDFs, and it will have a higher boiling and melting point than something similar that can't hydrogen bond. Shown right here is water. You can see this H is covalently linked to the O, and it interacts in an intermolecular fashion with an O, N, or F on another compound. So it says for each of the following substances, indicate whether hydrogen bonding through an available H, so it has to have an H, is an important intermolecular force. So if you have N2, you know the answer is no, because it doesn't have an H. HI, is that H connected to an N, O, or F? No, so that's a no. HF, that would be a yes, because the H is covalently bonded to an N, O, or F. The last two we have to draw out because you don't know where the H is until you draw it out. So in this one, CH3, and then a CHO. This is an aldehyde group. I don't know if any of you are in AP Bio, but you'll learn your functional groups there. This is an aldehyde group as opposed to the hydroxyl group that you see in alcohols. And now, which hydrogen is capable of hydrogen bonding in this compound?
The one on the far right.
Absolutely. You could have a hydrogen bond here between another methanol compound or with water. And in your lab, it asked if alcohols were soluble in water, and the answer is yes. And that's due to the intermolecular force between an alcohol and a water. You could get a hydrogen bond right there. Why is this structure incapable of hydrogen bonding?
Because the H isn't connected to an NO or F.
Perfect. Spot on. Alrighty? So alcohols can hydrogen bond with other alcohols, water, ammonia also. Ammonia is another one, NH3, that can hydrogen bond. So ammonia also is capable of hydrogen bonding. And this is a very difficult concept. I know in AP a lot of the kids really struggle with it. And I think the brief introduction that you get in honors will serve you well for future chemistry classes. The other example here is far more complicated. I did draw ammonia for you, so you saw that with the yes. This would of course be a no because H is not hooked into N, O, or F. These are far more challenging questions. I don't really think you would see anything that difficult at this level. But if you want to draw those out and examine, we can take a look at it. What I do want to bring you back to is biology. You probably recall that T pairs with A and C pairs with G for your DNA base pairs. What type of interaction is here, 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 and here? Hydrogen bond. Why do you think that an AT base pair melts at a lower temperature than a CG base pair?
Because it has one less hydrogen bond.
You got it. One less hydrogen bond. And that's where I thought you probably had seen hydrogen bonding. I'm not one to read a lot of books. I have a hard time sitting still. I think Cliff Notes were invented just for me. I know you now have bigger and better than when I went to school in regard to helpful study aids. But one book I would highly recommend is James Watson's book, where he talks about how he and Francis Crick discovered the structure of DNA. It's only a few hundred like maybe 100 and something pages, and it's a really little easy book to read. If you're interested, I have some copies in the back. So that one was particularly good. And also they made a movie of it. I think it's called Race to the Double Helix. And that was also very interesting. And I'm not a big science movie watcher. I'd rather watch Bing Bing Shoot 'em Up. But I do think that it really helped explain it. So that I did find very interesting. You find hydrogen bonding with proteins, enzymes, DNA, etc. So this is something that affects you each and every day. And I tried to give you a few images here. I just cut and pasted. So this is more than you need to know. We're not going to be playing with ion dipole this year or induced dipoles or dipole-induced. This is a bit much, but here's a hydrogen bond between the hydrogen of methanol and water. We drew this out for you. Here's a dipole-to-dipole interaction and London dispersion forces between two nonpolar covalent substances. When you have hydrocarbons, C's and H's only, you have a nonpolar covalent substance. So intermolecular forces form between molecules, and they help explain a lot of properties of substances. They are weaker than covalent bonds, but they do determine properties of molecules. And so they fit into the rubric that we mentioned at the very beginning of these two chapters. And you'll see a couple of very easy questions on your test. And I think almost every question that might be on there is right from your notes to keep it simple. Remember, figure out if the compound is polar or nonpolar, and then you'll know how to determine what type of IMF it has. Questions?